And we're back. Happy Thursday. Today I'll be switching gears a little bit with a focus on random variables and distributions. But before we begin, there's new reading by the 24th of September, which is a week from today being Thursday, in the third chapter of the main text, the Barron book, Probability and Statistics for Computer Scientists. The reading is section 3.1 to 3.2, pages 40 to 46. It's not a high page count, but you'll still need to invest about an hour each day in this class. So make sure, put some swagger in your step. Make sure you read every single day. Do a little bit each day to be successful in this course. Okay, so where we last left off, we talked about Bayes' rule, and we gave an example concerning flight arrivals and departures, and we said Bayes' rule was a method that we can use to compute the probability of one condition based on other conditions. And so in this, we said you need not have observed condition A given A. You can calculate the probability of some event given A from other conditions that you do have, observations you do have. And so we gave that example, and we used the definition of conditional probability to compute probability of arrival given departure and probability of departure given arrival. And then we turned around and recomputed probability of departure given arrival through Bayes' rule. And we found that we arrived upon the same result. We also then talked about this idea of B-slices as a way you can cleanly cut up or chop up a complex event so that you can define it as the sum of a bunch of pieces. And this is generally useful if you want to find or calculate the probability of that complex event. So let's turn our attention to random variables and distributions. Sometimes you have some base event, like a die roll, and the individual event that you observe, like small omega, they're not enough. For example, let's say you flip a coin k many times, and let's, for the sake of argument, k is always going to be even. So you're going to flip a coin 4 times, 8 times, what have you. One question that someone might want to ask is, what's the probability that the number of heads in k flips is going to be k over 2, that half of these coin flips are going to result in a heads, okay? And so we need a little bit more machinery, and we alluded to a random variable in a previous module as measuring something having to do, or measuring the raw observation or observation. And so let's define a function f, and f is going to take as a parameter, let me set the pen here, f is going to take as a parameter, we'll choose blue, it's going to take our event, be that a singleton event or a complex event, as is the case here, this flip of a coin k many times. So f is going to take as its parameter this event, and there are many functions over a complex event that you can imagine. It doesn't matter what that function is. You have to specify it, certainly, but it can be very many functions, anything that you could imagine. Now, a random variable, this is defined in the book, is a function, and that function is over the observable outcome from some file. And so we have our complex event, omega, small omega, and we execute our function, and we're going to call the result of that function, we're going to call that big X. Now, big X is a random variable. A random variable is nothing more than the result of some measurement or function over some event or complex event. And so let's look at this F. F takes as its domain the sample space. And this could be the sample space of a complex event, or it could be the sample space of a singleton event, a very simple event. But nonetheless, F takes this domain an event, right? One of the possible events, that's this little omega. So if we were to define our sample space omega, that's just some number of little omegas, where the little omegas, omega 1, omega 2, and so forth, omega n, are the individual events. Now, these could be complex events, like a string of heads and tails, k long, representing the outcome of k flips of a coin. Or they could also be simple events, like the outcome of the roll of a single die. So this function f takes as its domain one of these complex events, omega, little omega, and it has as its range, can be a number of things. It could be the set of real numbers. It could be the positive real numbers. It could be the integers. It could be some interval on the real number line between 0 and 1, etc. It's some range. And so this function is going to output a measurement over that complex event omega, and it's going to associate it with some number, like 5, right? So it is absolutely a function. And so the range of this function is considered the value associated with this random variable x. And so here, once the outcome is selected, the observable, I roll my die or flip my coin k many times, you then evaluate the function, and the result or value returned by the function is the value associated with the random variable x. So that's what a random variable is. Let's take an example, and let's imagine, if you will, we flip a fair coin. Now, flipping a single fair coin 3 times is the same problem as flipping 3 fair coins once each. We have 3 outcomes that can either be heads or tails for the first slot here, representing the first coin, the second coin, third coin, or it could be the first flip, second flip, third flip. But nonetheless, we're going to flip 3 fair coins, and so that fair is a loaded term. Well, you should all know what that means at this juncture in the semester. And we're going to define x to be a random variable, and this random variable is a measurement over the observations, the strings of head, tails, 3 many times. The observation, the random variable, is going to measure over that observation the number of heads. So that's the measurement. You're going to get a string heads, tails, heads, and that random variable x is going to say, all right, that's 1 heads, 2 heads. So it's going to be 2 if we compute that function over the string resulting from those flips of 3 fair coins of heads, tails, heads. And so if we were going to measure the number of heads, that's what this random variable takes on values. Let's examine all of the different values this thing could take on, and let's look at the probabilities associated with the different measurements that this random variable x can take on. Okay, so x equals 0, that means you have 0 heads. Well, how do you get 0 heads? That means it's the probability of x returning 0 or measuring 0 heads is the same as the probability of getting 3 tails, which is the same as the probability of getting a tails, and a tails. Okay? Well, what is this result? We'll calculate that in a moment, but let's first set up the different outcomes we can have for our random variable x. So if x equals 1, well, that measures the number of heads being 1 from that string consisting of some combinations of heads and tails. So there are 3 different ways we can do that. You can get heads on the first flip, tails on the second and third. You can get tails, head, tails, or tails, tails, head. Each one of these, if you were to measure the number of heads, it's 1. Okay? So the probability associated with your random variable measuring 1 heads or having a value of 1 is going to be the sum of each of these different ways you can have a single heads in your string of 3 flips of the coin. Likewise, if random variable x takes on value 2, we can have 2 heads in the first 2 positions, heads in the first and the last position, or heads in the last 2 positions. And again, the probability associated with random variable x taking on 2 is going to be the sum of all these different strings you can get of heads and tails resulting from the 3 coin flips. And then lastly, we have our random variable taking on the value 3. Now, there's only one way to do that, probability of heads in the first one, second one, third one, and we'd evaluate that probability. So if we were to look at this, each one of these flips is independent from one another. And we know that sample space omega has a cardinality of 2, heads and tails. And therefore, if we were to compute the probability from first principles, the probability of heads is equal to 1, number of favorable, over 2, or 50%. Likewise for tails, it's 50% as well. So now we know how to do that for a single coin flip. Let's examine this. And mind you, these probabilities as individual events, that observation, the second observation, the third observation, they do not depend on one another. They're independent. And they're independent because you're not saying, oh, if it's heads, well, I'm going to choose tails here. If it's tails, I'm going to choose heads here. That doesn't happen. There's no linkage between the two. They're independent. And so we multiply if we have three events together, occurring together. That's the same as an and. So we say that's the probability of the product of the probabilities of the individual events. So that's 1/2 times 1/2 times 1/2 is 1/8. Okay. So let's do that again here. Well, that's 1/2 times 1/2 times 1/2. Again, 1/2, 1/2, 1/2. So that's 1/8, 1/8, and again here 1/8. We add them up, we get 3/8. Likewise, same thing here. It's 1/2 times 1/2 times 1/2. So this expression is 1/8 plus 1/8 plus 1/8. That's 3/8. And then lastly here, it's 1/2 times 1/2 times 1/2. That's 1/8. Okay. And so we take all of these probabilities and we can summarize the behavior associated with the probabilities for each one of the outcomes of this random variable x that measures the number of heads. And so in this table, we have the random variable x, and then we have the probability that this x, this random variable, takes on a value. And so when you list out values that random variables can take on, you use the lowercase alphabetic character. When you talk about the variable itself representing the function, you use the uppercase. So random variable big X takes on a value little x, and that's how we note that mathematically in a general way. So what can the value little x be? It can be 0, 1, 2, or 3, many heads that this random variable big X takes on. And so the probability that random variable x takes on value little x equals to 0, that probability of taking on a 0, where little x is a 0, that's 1/8. So we had that from before. The probability that random variable x takes on value little x where little x is 1, that's 3/8. Where little x is 2, that's 3/8. Little x is 3, that's 1/8. And if we add them up, that's 1 plus 3, that's 4, plus 3 is 7, plus 1 is 8, that's 8/8, for a total of a probability of 1. So each one of these outcomes, 0, 1, 2, 3, of this random variable, that represents all of the different possibilities we can have for the random variable. And you'll note that the law of total probability holds true here. We have a total of 1, representing 100% probability. Either you're going to get a 0, 1, 2, or 3 value associated with this random variable that measures the number of heads observed from 3 many flips. And this table does something special. It takes this measurement, this random variable x, and it summarizes everything about it. You don't know what value for the random variable you're going to get until the observation occurs, that string representing the outcome of 3 flips, and then you apply this measure and you get that value. But we can list out all the possible outcomes of this measurement, this random variable big X, and we can also compute their probabilities going back to first principles that we've learned in a previous module. And so we have this catalog of the possible values your random variable can take on and the associated probabilities. Now, this catalog of all the values and the probabilities, that's called the random variables distribution. So this distribution then describes the collection of probabilities associated with the when can I see you again for each of the values that this random variable can take on, the result of this function. And so notationally, how you'd write this probability as a function, and you'd say P of x, where x is the value the random variable can take on that it would return, is equal to the probability, so P of x, probability of that random variable's value, probability of the value is equal to the probability that random variable big X takes on value. So this is the variable big X, and this is the value little x. And that's how we write it, definitionally, mathematically. So this function, P of x, has a name. It's called the probability mass function, abbreviated PMF. And you can think of the probability mass as a weight or mass. And this distribution then, this table listing all the possible outcomes and the associated probabilities, the associated weights, if you will, it tells you how the weight is scattered about or distributed among the different values that the random variable can take on. And you can think of a weight almost like a number representing some notion of importance or frequency. The more quote unquote important values of the random variable are going to occur more frequently. When can I see you again? The probability. So we take a random variable and we describe that random variable as measuring the number of heads that you see when you flip a fair coin 3 times, or you flip 3 fair coins. Now we can depict this as a graph, and when we depict this as a graph, on the vertical axis, on the horizontal axis rather, we're going to list out the values little x that the random variable can take on. So we said little x can take on values 0 heads, 1 head, 2 heads, or 3 heads. Now, the vertical axis is the probability p of x associated with each one of those values. So here for 0, we said it was 1/8, so we mark 1/8 here. For 1, it's 3/8. For 2, it's 3/8, and for 3, it's 1/8. So all we've taken here with this graph is just written out this table in a graph form, and you'll note that we have all the values, little x, in sequential order. It has to be some order. So let's note the shape. If we were to take a pen and draw an envelope that connects each one of these so-called mass points, note the shape of that distribution. So now, given that shape, we'll remove those mass points, those lines telling you how much probability mass or weight is associated with each outcome that the random variable big X takes on. We'll eliminate those mass points, and we just look at the graph which connected each of the mass points together. So we note the shape of this graph, and now the shape of the distribution is going to describe for us how this random variable x behaves. And by behavior, I refer to the types of values that it will take on with a repeated number of tries of this experiment of flipping the coin 3 times. You could also call it the dataness or the aboutness of x. The shape of this graph, the shape of this distribution, tells you about the behavior you'll observe for random variable x. Okay, so we have this catalog of values, our distribution, and then we have our graphs. Now let's suppose we have the distributions in graph format for 2 different random variables. On the left, we have random variable x, and it takes on 4 different values, 0, 1, 2, and 3, so that's our coin flip. And on the right, let's say we have another coin flip, and it's a weird type of coin, right? And y measures the number of times that other weird type of coin comes up heads if you flip it 3 times. All right. And so here, let me ask you a question. If we were going to wager on this, we're going to each bet $1, and if you could guess correctly where the coin is going to sit, or how many heads you'd have after 3 flips, you get to keep my $1. If you guess incorrectly, I get to keep your $1. Now, which one would you rather wager a bet on? Well, I don't know about you, but I would rather wager on this system X for coin number 1. Now, the problem with coin number 2 is that if you make a guess, there are many more ways to get it wrong, but if you look at the probability mass for this region, for outcome number 1 and outcome number 2, it's 3 times the probability of the 0 and the 3. So if you were to guess either the 1 or the 2, you'd be right more often than if you guessed either the 1 or the 2 for the second coin. And so the idea then is that the shape of these probability distributions give you information about how the underlying coin flip 3 times or flip of 3 coins behaves. For the X random variable system, coin system number 1, more of the time you'll see 1 head from 3 flips of the coin or 2 heads, but much less you'll see 0 or 3. Whereas for coin system number 2, that really weird coin, you flip it 3 times or you flip 3 of them, there's going to be equal representation for the number of times you're going to see a 0 outcome from that measurement for the random variable y, 1 outcome, 2 outcome, or 3 outcome. And so comparing the shape of these two distributions, and any two distributions, gives you insight into the differences in how the data behavior unfolds for the two systems. There are some times that you're not just interested in a singular outcome of this random variable. Sometimes you're concerned with an interval along X. And so in this case, we're not just concerned with the measurement outcome of observing 0 heads or observing 1 heads. We're concerned about measuring 0 or 1 heads as a set. And this kind of looks like a complex event. It behaves very similarly. So we need an extra machinery with our distribution to be able to handle these complex events, to put them together. And so this is a so-called cumulative distribution. And this cumulative distribution gives us the tools to be able to form complex events involving random variables. It allows us to specify intervals of values returned or taken on by the random variable. For example, maybe we want to know the probability that if you take a fair coin and flip it 3 times, or take 3 coins, flip them each once, what's the probability that the number of heads is going to be less than or equal to 1? So less than equal to 1 means that it could either be 1 or it could be 0. So how are we going to do this? Well, essentially, you're going to calculate the area under the curve. And for the cumulative distribution, there's a tool, call it the cumulative distribution function, or CDF. And what the CDF is noted as in the book is capital F. It's a function, and it takes a value x. And when you have f of x, x is a value taken on by the random variable. And the behavior or the semantics of the cumulative distribution function, or CDF, is that it takes the probability that your random variable returns a value or is associated value that's less than equal to that parameter x that was passed in. And so in this case, if we said f of 1, that represents the probability of seeing 0 heads, measuring 0 heads, or measuring 1 head. And how you calculate that is you sum. You sum each one of the values up to and including x in this particular case. And so this cumulative distribution function, or CDF, is the tool we use to talk about complex events described by random variables. All right. And so this looks a lot like the probability of a complex event, and it is. And essentially, you're doing some equivalent to what the union was accomplishing. But we don't use union here because we don't have sets. Remember, a random variable is a function, and that function returns a value. And so if we want to traffic in complex events, we need the tool of addition in order to combine those probabilities together, i.e. combine those proportions, when can I see you again, associated with each one of the outputs of this random variable function. And so another way you might compute this, if it's already come to mind, we're adding. And what this adding does is it literally takes the probability distribution function curve, if you will, and it takes the area or measures the area under the curve. And so other tools we have from calculus for measuring the area under the curve is the integral. And we'll find in a future module that you can use the integral to build complex events and evaluate their probabilities whenever that random variable takes on a real value. It's a so-called continuous random variable. And we'll get into that in a little bit later. And so what happens if your interval is one of these notches? And so before, when we took this interval, we said from the smallest value that the random variable can take on up to a particular value, okay, in sorted order from left to right on the horizontal axis. But what happens if we have a notch here? We have an interval. How do we compute this cumulative distribution function if we're dealing with intervals? How do we compute arbitrary complex events that don't involve the endpoints going all the way up to a certain value, integrating or summing? Well, an example for that is listed here. Imagine if we wanted the probability that the number of heads we observe from 3 flips of a coin, that's the CDF, is between 1 and 2. That's a little bit more difficult. So let's think about this. Well, if the tool we have is the CDF, cumulative distribution function, what is this notch? This notch can be formed by taking the area under the curve from the extreme left, the smallest value, up to the 2, and then subtracting out this region, which is the cumulative area under the curve from the extreme left value, smallest 0, up to a 1. And so we can use this CDF, cumulative distribution function, to effectively subtract out what we don't want to leave this notch, this gap, this interval for which we're trying to form a complex event. And so the difference between cumulative distribution is the probability of a notch, an interval. And so here we say the probability that a random variable x is between a and b, where a and b are values, so x takes on the value greater than a, less than equal to b. That's nothing more than the CDF evaluated at b, and then you subtract from that the CDF evaluated at a. And so here on the distribution in graph format, the red shaded area is the area under the curve for f of b. So in this case, b is 2 and a is 1. And then the green region, shaded region, is the area under the curve for f of a. And so in this case, that would be the CDF evaluated at 2 minus the CDF evaluated at 1. And that would be the probability that your random variable x, measuring the number of heads, is greater than 2, greater than 1, and less than equal to 2. And that represents the area under the curve for whatever is left when you perform that subtraction. It's this region, that interval, or notch, if you want to call it that. Okay, and so now we have both the CDF, we have this difference that allows us to compute the complex events probability for arbitrary intervals for outcomes of our random variable. All right, so we'll end with this last part. We have 2 types of random variables. One is called a discrete random variable. Now, a discrete random variable is some random variable whose function, the range of that function, is finite or countably infinite. So in the case of our random variable x measuring the number of heads in 3 flips, well, that range of that random variable f is the values 0, 1, 2, and 3. Now, this particular range, if we were to count all of the different values, it's finite. You can put it in one-to-one correspondence with the set of naturals, and it ends. It ends at 4. So this is the first item paired with 1. This is the second item. This is the third item. And lastly, this is the fourth item. So yep, the cardinality is 4 for this range of that particular random variable. There are other random variables that are not finite, but you can still count them. And those are called countably infinite random variables. And both of those, whether finite or countably infinite, they're called discrete random variables. And so for a discrete random variable, when you take the CDF, both cumulative or for an interval, you use the sum for such a CDF. You have another type of random variable where the range for that random variable is the set of real numbers. Such random variables are called continuous random variables. And more correctly, you cannot count the range here. You can't put into one-to-one correspondence with the naturals. That range is so-called uncountably infinite. It's so big, there's so many, that you can't put the individual elements of this range in one-to-one correspondence. Now for these, when you're putting together those individual outcomes that the random variable takes on, the probabilities, you take the area under the curve using the integral. And so we're going to be using the tools of calculus, specifically the integral, and to some lesser degree, the derivative for certain purposes, in order to construct complex events for random variables whose values that they take on are uncountably infinite, i.e. from the set of real numbers. Okay, so with that, I'm going to end there, and we'll pick back up next time with random variables. Until then, please have a great weekend, and please stay healthy and stay safe. I will see you next week.